Hello, everyone. Thank you for joining to hear my presentation entitled From Theory to Action, Developing and Evaluating Learning Analytics for Learning Design. The study that I'll be sharing with you today was completed in collaboration with my colleagues Yanis Dimitriadis from the Universidad de Valladolid, who's also in the Zoom room with us today, Allison Bradford and Marcia Lynn from the University of California at Berkeley. The study was completed over a course of 2 academic years and represents the outcome of using theory to guide the learning analytics development and evaluation process. The outcome was a learning analytics solution that gave researchers and teachers the insight needed to optimize student learning. The outcomes and lessons from this study also culminated in the development of a framework for developing and evaluating learning analytics for learning design. I'll be sharing that with you at the end of the presentation. I'll begin the presentation by describing the theoretical approach and research context. I'll then describe the study design, present the study findings, and then share with you the framework that we developed. And then I'll end with a discussion of the next steps and future directions. According to the definition of learning analytics provided by the Society for Learning Analytics Research, the central purpose of learning analytics is to support the understanding of learning and the optimization of the learning context. Learning analytics research identifies numerous challenges associated with developing learning analytics that accomplish this purpose. Heavy reliance on data literacy for learning analytics interpretation, as identified by Al-Haddad, 2018. Or that data selection is often driven by convenience factors rather than learning theory, as Raymond in 2016 points out. Lockyer et al. In 2013 identified the misalignment between learning analytics and learning design as a particular challenge associated with the field. Yoner and Ginther in 2018 identified a limited focus on actionability as another challenge. The central claim that we make in this paper is that to be effective and really overcome these challenges identified in the literature, the learning analytics must be grounded in a theory of learning and implementation. The learning theory that we use in this study is socio-constructivism as operationalized in the knowledge integration framework. And really this framework, as well as this learning theory, holds that learners come to a learning context with prior ideas, and those ideas need to be elicited. The learner needs to be given opportunities to discover new ideas or have ideas added to their repertoire, and then have moments and opportunities to really distinguish between those ideas as they move toward connecting those ideas into a coherent knowledge base. The implementation theory that we use for this study is the LAID framework, or the Learning Analytics Implementation Design, put forth by Wise and Vidisek in 2017. And this framework has 3 core principles. 1, coordination, and that principle is further divided into conceptual coordination and logistical coordination. Conceptual coordination relates to really the alignment between the learning analytics and the learning design. And so in what ways do the analytics reflect and connect to the learning objectives? The logistical coordination refers to how and when those learning analytics are going to be accessed, made available, used by the user. For absolute comparison, the student data is compared to a standard. So that could be a right or wrong answer, a rubric, criteria, or things like that. Relative comparison deals with comparing across categories, like from one student to the next or one class period to the next. The customization principle has to do with the opportunities that the user has to customize the learning analytics, how they're presented, how they're viewed in a way that accommodates that particular user. Throughout the process of developing the learning analytics for the study, we drew upon the Orchestrating for Learning Analytics framework, or the ORLA framework, put forth by Prieto et al. 2017. And in particular, the inter-stakeholder dialogue principle. And really this asserts that all of the stakeholders in the context of this study, it was the researchers, teachers, and system developers, need to be in communication during the development process so that the resulting learning analytics solution is something that can meet the needs, align with the values, and work within the constraints of all of the stakeholders. This principle of inter-stakeholder dialogue also calls for a liaison to mediate that dialogue. And for the context of this study, I was the liaison that mediated conversations between each of the stakeholder groups. Taken together, these three elements represent our theoretical design approach, where our learning theory represented by KI and our implementation theory represented in the LAID framework combine through the development process, which is guided by the Euler framework, to generate a learning analytic solution that has the desired outcomes of being interpretable, actionable, implementable, and also improve student learning. We chose design-based research for our methodology, and as Sandoval 2004 and Riemann 2016 point out, design-based research really draws heavily upon theory, and the theory really drives the design, and it's in the first cycle of that design where it's implemented and analyzed that lessons are learned and their implications for that theory, and then that leads to us multiple other iterations or cycles of design, implementation, and analysis. For this study, I'll be focusing on 2 cycles that took place over the course of 2 years. And so our study addresses the following research questions. Are the data used to generate learning analytics useful for understanding student learning and optimizing the learning design? And our second question, is the resulting learning analytics solution useful for informing pedagogical action? So the study context is the web-based inquiry science environment, which is an online platform for designing, developing, and implementing science inquiry units. In particular, we use a global climate change unit, and this unit is aligned with the state standards where the study was conducted. This unit consisted of 8 lessons, with the primary learning goal of supporting students to understand the role that the sun plays in warming the earth and the ways that human activities might influence Earth's temperatures. The learning design for this global climate change unit aligned with the knowledge integration framework. Taking, for example, lesson 2, students are engaged in the process of knowledge integration, starting out with having their ideas elicited, their opportunities through interactions with animations and experiments and diagrams and data to add new ideas, and then opportunities to wrestle with those ideas to figure out which ones are the most productive for developing an understanding of the phenomenon, and then lastly to end up the lesson with connecting and synthesizing all of those ideas into a coherent whole. So what we chose to develop the learning analytics from actually came from previous work where teachers identified that one of the WISE unit features, or this multiple number of attempts feature, could provide them with useful information regarding student engagement and performance. The way this feature works is that the unit designer will set the maximum number of attempts for a given multiple choice answer. So in this case, the attempt limit has been set at 4, and so students will have 4 opportunities to submit an answer for this response. So to make this feature more consequential for learning, first we decided to reduce the number of attempts to 1 minus the answer choices. So for this example, there are 4 answer choices, and so the number of attempts was set to 3. We also decided that rather than activating this feature for all of the multiple choice items in the unit, we decided to restrict the activation of this feature to the 7 distinguishing ideas items located throughout various points in the unit. We chose the distinguishing ideas steps because previous research had indicated that this was a critical juncture point in the learning process, a step where students needed the greatest amount of support. So we set out to answer the question, are the data used to generate the learning analytics, i.e. the data from the multiple number of attempts or MNA feature, useful for understanding student learning? So to address this question, we evaluated the log data and student work associated with 479 students across 5 teachers, all located within 1 school, and we generated a logistic regression model. For the logistic regression model, we chose just 2 of those 7 multiple choice items, and then also an open response item from the unit. We chose these items because they address the same concept of the sun's warming effect. The first multiple choice item, the maximum number of attempts was set at 3, and then the second item, the number of attempts max was set at 4. So after completing these distinguishing ideas steps, students would engage in a connecting ideas explanatory response where they would have to explain how the sun warms the earth. For the regression model, we also included a pretest item, which also related to this idea of the sun's warming effect. So for those open response items, the one in the unit as well as the pretest item, we evaluated students' responses using a knowledge integration rubric, which prioritizes the links that students make between normative or conventional science ideas. So for the regression model, we created 2 cutoffs, the first between score levels 2 and 3, which distinguishes between responses that do and do not contain normative science ideas, and the second between score levels 3 and 4, which distinguish between responses that do and do not contain linked normative science ideas. For our response variable, we chose high performance on the unit embedded open response item. And for our explanatory variables, we chose the level of attempts needed. So low, students were able to answer both multiple choice on their first attempt. Medium, they needed 1 or 2 attempts to answer both correctly. And then high, which would correspond to students submitting multiple incorrect answers or needing lots of attempts before getting the answer correct. And then we also used the performance on a pretest to control for prior knowledge, and then also had a teacher control for the pedagogical variation across the teachers in this study. And the results from the regression model indicated that indeed the number of attempts that students needed on these distinguishing ideas predicted whether or not they would score high on that KI rubric, with a subsequent explanation item where they had to describe how the sun warms the earth. So you can see for students needing 4 to 7 attempts, they were 75% less likely to get a high score on that subsequent open response item. And as might be expected, the students who at the pretest were scoring at a high level on the KI, they were 4 times more likely to score high on that unit embedded explanatory response. And then also was interesting that with the teacher variable not rising to a significance level of 0.05, pedagogical variation was not a factor for determining student performance. We then explored the data to address our next research question of whether it could be useful for optimizing the learning design. And so, again, for these 479 students, we evaluated their log data and student work associated with the 7 distinguishing idea steps to see their navigational patterns. One of the features of these distinguishing idea steps is that they have automated feedback when students select an incorrect answer. And this automated feedback is a direction for students to go back and watch an animation, which would create an opportunity for them to get the ideas that they needed in order to really understand the phenomena. We noticed that despite being directed to do so, students were not revisiting the animation, which was located on a different page in the unit. We decided to place the add ideas item and the distinguishing ideas items on the same page. So now that we validated that our new implementation of the M&A feature was both useful for understanding student learning and optimizing the learning design, we engaged in an inter-stakeholder dialogue with the system developers to discuss how to create analytics using this data that would be available for teachers when they're using the Global Climate Change Unit within the WISE platform. During that dialogue, the system developers shared that they would not be able to develop a system integrated analytics report given their other development obligations. And so they suggested that we generate a report that could be emailed while they made preparations for system integration, which was going to take about 6 months. So this actually highlights one of the challenges associated with this type of work, because even with a dedicated team of system developers, there are constraints that need to be worked within. So guided by the principles of our learning and implementation theories, we, the researchers, developed an email version of the analytics report. So we created a Python script to extract and analyze the log data associated with the 7 distinguishing ideas steps, and generated a report that would be provided to teachers within 24 hours of the time that 50% of their students completed the item. And the report was to help teachers answer the question of how many students or groups chose the correct answer on the first attempt. Of those who needed multiple attempts, what was the most commonly selected incorrect answer? And what were alternative incorrect answer patterns? And so with this information, we also provided them with the student IDs so that they would know which students might need additional support. And as I mentioned, we really drew upon our theories, and in particular here, the implementation theory, the laid principles. We implemented the conceptual coordination, which brought to focus the learning design and the learning context. What were the learning goals that students were being asked to meet? What was the prompt? And then we also provided teachers with that data, and we presented it in a way that would allow them to engage in both absolute comparison, how many of their students got the right answer versus the wrong answer, and then also relative comparison, so across periods and identifying particular students who answered in particular ways. We also included a researcher's insight, which was our synthesis based on our analysis of what might be leading to students choosing a particular pattern of incorrect answers. And so this was also included in the response. And so for each of those 7 items, this response was provided to teachers. And we sought to answer the question, is this learning analytic solution useful for informing pedagogical action? And so we conducted inter-stakeholder dialogues with the 4 teachers in this part of cycle 2 of the study. And then we also did a classroom observation with 2 of those teachers. And so what we found is that with the same types of analytics, there are different pedagogical actions, but there was action. When Ms. Carrington got the report, she acted by helping her students understand how their prior knowledge could lead to misconceptions. And Mr. Lewis's actions in response to the analytics took the form of identifying which students used all of the attempts without answering the question correctly, and then creating these one-on-one conferences with them to provide them with that focused individual attention. On the other hand, Mr. Schofield took the action of creating smaller groups where the students can talk amongst themselves and provide explanations and rationales for why they might have chosen a particular incorrect answer. And then Ms. Huey decided actually not to act, expressing that she felt that the automated feedback that was associated with the distinguishing ideas items was sufficient of support for students. So she decided that no further action by her was needed at that time. Interestingly, this theory-grounded approach to developing learning analytics can also seem to improve teacher practice. So one teacher noted that she recognized how an activity that she did in the week prior might have been responsible for her students developing a pretty strong misconception. And in light of that, she said that she would definitely be making changes to that activity for the next year. And then another teacher noted that he would be implementing, in response to the data and the patterns that he was seeing, more pre-activities that would help students really understand their background knowledge and what they will be bringing before engaging in a unit. So what the actions that these teachers took helped us to see is that understanding the learning design is actually really critical for being able to take pedagogical actions in response to learning analytics. The teachers who were able to take pedagogical action in response to the learning analytics report, those teachers felt comfortable with the unit. For Ms. Hui, who decided not to take further action, she also decided not to receive any more reports. And she stated that the primary reason for her decision was that she didn't yet feel comfortable using the unit. This really highlights an opportunity to foreground even further the learning design in the learning analytics report. So taking together the results and lessons from this 2 academic year design-based research study, we propose a framework for developing learning analytics, and it's the theory-grounded learning analytics development and evaluation framework, or the TGLADE framework. And so this framework has 3 principles. And the first principle is that you should use a learning theory to guide data selection, analysis, and validation. So for example, in deciding what data we were going to use to develop learning analytics, we really drew upon the knowledge integration framework in deciding which types of items we would activate the feature on in order to gain insight into the learning process. Our learning theory focused on integrated knowledge led us to analyze that data in a particular way to really to validate whether or not it was providing insight into that knowledge integration process. The second principle is to use an implementation theory to guide the feature development and evaluation of the learning solution. So for example, we drew upon the LAID framework to present the data that would create opportunities for teachers to engage in absolute comparison and relative comparison so they could really probe the data and gain additional insight into their students' learning and the needs that their students might be having. And the third principle is to use theory as an arbiter during the development process. For example, when we were trying to decide how to make the feature most consequential for learning, the system developers felt as though since the capacity was there to activate the feature on all of the multiple choice items, that was the route that we should take. Some of the teachers agreed, and others felt like we should be more selective, but didn't really care which type of item it was. And so the researchers, with a stronger grounding in the learning theory, felt like it would be most appropriate to activate that feature on the items that would give additional insight into a critical point of the learning process, the distinguishing ideas step. So in this case, it was the learning theory that served as the arbiter for helping us make that decision. And so in terms of our next steps, we are going to be looking to augment the implementation theory with data storytelling principles from Echeverria et al. In 2018, with ideas of reducing the text or connecting even more to the learning design. And then also to integrate the report into the WISE system, and that's actually would be our third cycle, and create an opportunity for us to further emphasize the customization principle and develop a customization interface to support action. So we've generated a mock-up of what a system integrated report might look like. And so again, drawing on the LAID principle, conceptual coordination, really foregrounding and highlighting the learning objectives, the standards, the prompt to anchor teachers' attention to what those learning objectives are. We also have restructured into a more graphical, visual representation to more quickly and easily support teachers in engaging absolute as well as relative comparison. And then again, with this mock-up, we really wanted to create an opportunity to draw upon and implement the customization principle. And so introducing this idea of this target percentage of students who would answer correctly on the first attempt. And then also looking to this key insights section, the goal is to summarize the information, but then leave open how teachers would respond, because as we saw in the study, teachers will respond based on their own teaching practice and the constraints and opportunities in their classrooms. And so our future directions, we are looking to expand this learning analytics for other assessment items, including additional aspects of student data. And then also to look at what's the effect of teachers' actions on student learning. So I would be remiss to not recognize that this work is done in the context of a research team with our teacher partners. And so I thank you for your attention and welcome your comments and questions, which either I or Giannis Dimitriadis will be available to answer for you. Thank you.